Okay, let's go ahead and start. Thank you all for joining the Matrix AI Consortium seminar speaker series. Today we have Dr. Matthew Hirn with us. He's an associate professor at Michigan State University in the College of Natural Science and the College of Engineering. And he holds a joint appointment between the Department of Computational Mathematics, Science and Engineering and the Department of Mathematics. And he's also a member of the Center for Quantum Computing, Science and Engineering. And at MSU, he's the scientific leader for the Complex Data Analysis Research Team. His research interests are in developing machine learning algorithms for the analysis of high-dimensional data. And he also likes to develop new algorithms with mathematically provable guarantees, in addition to using these algorithms to push the state of the art, whether it's in quantum chemistry, whether it's in material science, biomedicine, and several other fields. It's a pleasure to have Dr. Hirn join us today. Thank you so much. And the floor is yours, Dr. Hirn.
Oh, great. Well, thank you very much for the kind introduction and the invitation. It's really a pleasure to be able to give this seminar virtually, but nevertheless, it's a great pleasure. So what I want to talk about today is some work that we've been doing in my group on convolutional neural networks and some mathematical models we've been developing for them through the language of mathematical signal processing. And so I suppose for this audience, many of you are familiar with deep learning. And potentially even convolutional neural networks. But just here's a very quick primer. A ConvNet, such as the one that you see here, is a particular type of artificial neural network, illustrated here down in the corner, which is designed for signal-based data. And by signal-based data, I mean things like one-dimensional time series, maybe an audio recording, or perhaps a two-dimensional signal like an image, which is very natural. Or even, as we'll see down the line, three-dimensional signals, which might represent three-dimensional physical systems. And so what it does, though, that is a bit different from a standard artificial neural network, though, is that it leverages this underlying geometric structure to the data. The fact that you have pixels in an image which are arranged in a spatial pattern, for example. And it does so through the use of convolution operations, which means fundamentally that the inputted image in this case is filtered through a bank of filters which serve as feature extraction mechanisms for the image. It does this through many different layers of the network. And at each layer, there's also then some nonlinearity. And at certain stages, there's also something called say a pooling operation, which compresses the size of the data, thereby allowing one to obtain multiscale representations of the inputted signal data. So anyway, here's a very popular convolutional neural network called the VGG ConvNet. And from our perspective today, the things that we're really going to want to focus on mathematically is the idea that by using convolution operators, as opposed to sort of general fully connected layers, a ConvNet is leveraging the data structure, the fact that it is signal-based. And through the depth of the network and these pooling operations, it's obtaining a multiscale representation of this data that also encodes certain types of invariance properties with respect to the task at hand and the data that's being processed. And so this has been very successful in the machine learning literature and in the machine learning community for a variety of different tasks. One that many people are familiar with is image classification. For example, on something like the ImageNet database, in which you have millions of different images. You train your net on some, you classify others. Of late, though, folks are also interested in not just classifying images, but also generating new images, so-called generative models. Texture synthesis, which is something I'll come back to later in this talk, is a particular flavor of generative model focused on texture-like images. Here, convolutional neural networks are revolutionizing this field. In the physical sciences, inverse problems have also not been immune to the charms of neural networks and convolutional neural networks in particular, in which one is seeking to recover, say, high resolution, high fidelity images from limited measurements in some sort of physical or biophysical situation. Here again, ConvNets are really pushing the state of the art. Coming back to forward type problems, one can work in physical sciences, say in particle physics, for the prediction of materials properties, for the prediction of potential energies of molecules in chemistry, convolutional style networks, but which are maybe adapted to data that doesn't quite have the rigid structure of an image, but which does have positional information such as the locations of the particles, which can be leveraged in the design of the network, have been very successful in carrying out some of these sorts of tasks associated with, again, chemistry or material science. This is also something I'll come back to later in the talk. And indeed, one can push this even further by working on, say, manifolds, which might represent two-dimensional surfaces in 3D, for example, in the computer graphics community. One can generalize the notion of a filter, one can generalize the notion of convolution to these locally Euclidean structures, and understanding sort of the mathematical ways in which to do that, and also the mathematical implications for the nature of the network is an interesting problem. And one can even push it further to just general graphs, right? So you just have data, some of the data points are connected according to edges in the graph. Maybe you want to process different signals over this graph. Maybe you have many different graphs that you want to process. Maybe you want to predict information about certain nodes in the graph, but nevertheless, it's not a Euclidean structure, but there is some structure here in the data given by the graph and the edges that connect different vertices. One might want to leverage this information when building a neural network, and indeed graph neural networks or graph convolutional networks aim to do just that. So that's all to say anyway, there's a lot of different work going on in sort of convolutional style networks, construed broadly, right, to go beyond even just traditional image processing. And as such, folks are very much interested in trying to understand, why do these things work so well, right? And there's been numerous different approaches for this, including on the more mathematical side, approximation theoretic approaches. One can, train a network and then go back and look at the filters and try to understand what types of information they're extracting from the data on which they've been trained. Even folks in topological data analysis, for example, have gone along this route in recent years, as well as sensitivity analysis type approaches in which one tries to understand, for example, in image classification, which parts of the image did the network focus the most on in order to make its classification prediction. These are all very good, and they all have their merits. They are fundamentally, though, based upon or motivated by particular tasks, right? It's the approximation theory. You want to approximate a certain function which represents the label function. When you're analyzing the filters of a network that's been trained, it's been trained for a particular task. Sensitivity analysis is in the same vein. You're analyzing how sensitive the network is to different perturbations or regions or areas within the original data, but that network has been trained again for a certain task. In this talk, we're going to take a little bit of a different approach. We're going to describe a mathematical model for convolutional neural networks called a wavelet scattering transform that is not task-driven. In other words, we're not going to have some task which is pushing us to learn a certain type of network, but rather we're going to construct it by taking advantage of what are in some sense first principles data properties. Things like the data structure. Do we have signals? Do we have images? Do we have manifolds? Do we have graphs? Invariance to certain group actions then. For example, in many image processing tasks or even signal processing machine learning tasks, the action of a translation or a rotation is sort of something of interest in almost every task. We can phrase these in terms of group actions. We also want our network to be stable, though, to deformations. This is a universal property that almost anyone would want in their network. If you have a small perturbation of your inputted data, whether it be a signal, whether it be an image, whether it be a graph, whether it be a manifold, you would like to know that your network is not going to drastically change its output class label or its output representation of that input. And so having mathematical guarantees with respect to the stability of the network is important here. And lastly, multiscale decompositions, right? The depth of the network implies a certain multiscale aggregation of information of the original signal data, and we would like to take advantage of that as well. Okay. And so as the name, and so the outline then of the remainder of this talk is going to be the following. I'm going to describe here at the beginning and through the middle of the talk a general theory for convolutional neural networks based upon the notion of a wavelet scattering transform, which, as we'll see, basically means we're going to take those properties that we just listed, think about them from the perspective of signal processing, and by sort of following our nose in terms of how do we sort of encode all of these properties at the same time, which are in tension with one another to some degree, we'll see that the architecture of a ConvNet naturally arises. And then we'll sort of zoom in a little bit onto 3 different application areas. We'll see how one has to sort of adjust the nature of the network in each of these particular cases. One for machine learning and material science, one for texture image generation, and one for just a genuine inverse problem in multi-reference alignment, sort of harkening back to a few of the types of fields that we saw at the introduction. And then if time permits, I'll briefly discuss how these ideas, in fact, are more universal than even just for signals, but in fact can be generalized to manifold-based data and graph-based data. Okay, so signal processing. Signal processing often casts things in the language of frequency decompositions of the signal. I'm going to use this butterfly image as sort of our prototypical signal throughout this part of the talk. Here's just some basic notation. I'm going to let T denote the torus. What does that mean? Well, it just means it's an interval. I'm picking -pi to pi. And then I'm going to look at images X or signals X more generally, who are supported on a d-dimensional torus. And so if that's a little too abstract for you, that's fine. Just think of D being 2 and X is an image. And that's sort of, as I mentioned, the prototypical example we're going to have throughout. What does Fourier analysis say about all this? Well, Fourier analysis then decomposes these types of signals in terms of their harmonics. And so we have an orthonormal basis of harmonic functions consisting of complex valued sinusoidal functions that oscillate at the frequency k. Okay, and so these are just a real part of a cosine and an imaginary part being a sine wave. The Fourier transform then says, well, if I want to encode the frequency content of my signal X, I do that by interproducting it with these different complex sinusoidal functions, which is then given by this formula here. And this is a genuine complete representation of the signal X in the sense that I have an inverse Fourier transform, meaning that I can recover X by knowing all of its Fourier coefficients. So this is a genuine, just another way of representing the signal X. And so here, for example, here's an example of that, right? So here is our butterfly image on the left. Each index U here represents a pixel. Here on the right is, well, the modulus of the Fourier transform because it's complex valued. I didn't want to visualize the real and imaginary parts separately. But here is the modulus of the Fourier transform of X. Each little dot here represents a different frequency K. And this is just another, up to the modulus factor at least, this is just another representation of the signal X. But it'll often be a useful one for us in terms of trying to understand what's happening. So again, that's all to say, rather than thinking about X in terms of its pixels, I can think about it in terms of its frequencies. And the first question I want to ask here is, which part of X is going to be invariant to translations and rotations? And the generic answer in terms of the frequency representation of such a signal is going to be the 0 frequency of X. And this is just, and one can see this because, well, the 0 frequency of X consists of just the average pixel value of X. And so certainly if you were to translate your image, again, periodically, let's say, so that we're not like losing any of the pixels, or we were to rotate our image, we'd have all the same pixels. They would just be translated or rotated. Of course, the average pixel value of X is not going to change. It turns out, though, that one can sort of loosen this a little bit and sort of generalize this idea to encode notions of quasi-invariance. And so once, in keeping only the zero frequency is rather limited, one could instead say, why don't I try to keep sort of just some of the low frequencies of X? So that is to say, I've taken my image, my butterfly image, I've computed its Fourier transform. Rather than just keeping the zero frequency, which is here in the middle, why don't I try to keep, say, the low frequencies in some ball around the zero frequency? That would be represented by this operator here, AJX. One could even do something a little more subtle, which is to say, well, instead of just having a hard cutoff function here, maybe I want some kind of smooth cutoff function. There's various mathematical reasons one might want to do this. That then is through the use of what's called a low pass filter phi, which basically sort of modifies this series here, which you'll notice here cuts off the frequency at 2 to the j. So that's, say you have that basically means you have a radius of 2 to the j here. This one basically says, well, why don't I have sort of a smooth cutoff, right? So in other words, basically it's not a hard cutoff, but it's a smooth cutoff. But nevertheless, it effectively is just keeping the low frequencies of the signal X. It turns out that when you keep these low frequencies of the signal X, you obtain a type of quasi-invariance. And so that's what this theorem here says. And actually, on top of invariance, you actually obtain a stability as well. So you remember from the sort of different properties we wanted invariance, we wanted stability. This is sort of indicating one mechanism by which to obtain these properties. So let's say that zeta is a diffeomorphism, and we let zeta act upon the signal X through this operator here. So this basically is going to deform your butterfly image in some fashion. We want to compare the low frequencies of our original signal X, our original butterfly image, compared to the low frequencies of the deformed version of it. And what this theorem says is that they can't differ by too much. In particular, they're going to differ by sort of the maximum displacement of that diffeomorphism. What is the part of the image that gets deformed the most? As well as then some other term here, k of zeta, such that if zeta happens to be an isometry, like a rotation, like a translation, in fact, this term will be 0. And so what this says here then is that basically, if zeta happens to be an isometry, this then gives us a controllable amount of invariance with respect to that isometry. If we let j, for example, go to negative infinity, which means that we're just going to keep the 0 frequency, if you sort of think about that. So if I let j go to negative infinity, this part here then becomes 0. That means I'm just keeping the 0 frequency. Sure enough, this theorem will say we get full invariance, as we observed on the previous slide. On the other hand, if we want to keep a bit more of the frequency content of the image, and we'll see reasons why we might want to do that in a second, this says that, okay, that's fine, then you obtain a type of quasi-invariance with respect to the original signal. And furthermore, if your zeta here is a more general diffeomorphism, then you have a type of stability. And we'll come back to more specific versions of this later. So let me illustrate to you what's happening here, right? So here's the original butterfly image. Now I've basically kept only the low frequencies of it via a low pass filter. So the way that's done is through convolution, right? So that's what this operator here is computing. So this is going to keep the low frequencies of our image X by convolving it with this low pass filter phi sub j, just as on the previous slide. And I can vary j, right? I can decrease capital J, which means I'm keeping successively fewer and fewer frequencies of the original image. In this last row here, you then see what the filter itself looks like. And you can see that it's increasing in size, which means that effectively it's computing larger and larger local averages with respect to each pixel. So in the case of, for example, this image here, each pixel gets locally averaged in a small neighborhood because the size of the filter here is rather small. The image that you see is pretty reflective of the original image. On the other hand, in this image here, every pixel was averaged with a huge neighborhood of pixels because of the large size of this filter. And you can indeed see that that significantly blurs the image. What the theorem on the previous slide says is, well, that this image, right, has very strong invariance properties. It's nearly invariant, and it's going to be also very stable to diffeomorphisms of the inputted butterfly. Indeed, if I were to deform the original butterfly image, you'd be probably pretty hard pressed to see that deformation in the blurred image if that diffeomorphism is not too large. Okay, very good. So what have we done then? Well, we've said that, look, we've decomposed our signal X, right, into low frequencies, either by some cutoff like here, or you know, by some convolution. Let me make that a bit bigger. Or by convolution, more generally with a low pass filter. And then we also have here high frequencies, and together the low plus the high gives us the signal X. We've observed that the low frequencies are both stable and invariant with respect to isometries, or even more general diffeomorphisms in terms of stability. But these high frequencies, it turns out, which contains the remainder of the information in the original signal, not stable and they're not invariant. In the language of invariance or isometries, they would be equivariant, but not invariant. And that's, you know, all of the different information outside of this ball centered around the zero frequency, which is significant, as one can see from this image. And so now we have sort of two options at play. One is to say, look, well, the low frequencies of our more signal have a lot of various properties, quasi-variance, stable to diffeomorphisms. Maybe that alone is going to give us a good enough representation of our inputted signal data. However, if one then takes this representation consisting of only the low frequencies and pushes it into some downstream tasks such as image classification, one's going to be in hopes for a good result. One might be in for a bit of a rude surprise when the classifier turns out to be not so good. The reason being, of course, that in order to get this nice invariance and stability properties, as you saw, we had to significantly blur the image. And while that makes it stable, it also means that many different images, or more generally signals, can be conflated. If we don't want to conflate so many different signals, you know, potentially even signals from different classes, we need to then go with option 2, which is to figure out how to keep the high frequencies, but transform them in a way that gives us a stable representation. And what I want to argue over the next few slides or so is that this is going to imply very naturally a lot of the different aspects of a convolutional neural network. And so there's going to then be two ingredients, which we saw before at the outset of this talk. One is going to be the use of multiscale decompositions of the data. Now, while a network gets this through depth and pooling operations, we're going to get this through wavelet transforms, which I'll describe here in a second, although we'll see where depth comes into play as well. The second thing that's going to be very important is through nonlinear transformations. For example, rectified linear units, absolute values, moduluses, sigmoidal functions, and so on and so forth. We're going to see how these two ideas work together in tandem to obtain a representation of our inputted data X that is both stable with respect to general perturbations and diffeomorphisms, invariant with respect, or quasi-invariant with respect to, say, translations or rotations, but also is very expressive and able to separate out different classes of the data. Okay, so let's begin with multiscale wavelet transforms. So you may recall that we've decomposed our signal X into low and high frequencies. And we're going to make the following observation, which can be made precise mathematically, that the higher the frequency, the more unstable it is. So if you deform your image X, then the higher these high frequency components, the larger K is, the more unstable in some sense they're going to be with respect to this deformation. And so what we're going to do is we're going to group them in a multiscale fashion, which is to say that within the high frequencies, the sort of lower end of the high frequencies will group into smaller groups But within the sort of very high region of the high frequencies, we'll group those into even larger groups. This will help us obtain a stable representation and can sort of be thought of as signal, like a way of obtaining, this will be the sort of multiscale aspect of our representation. And so how do we do that? Well, we take these high frequencies, we decompose them into these delta jx's. What does delta j do? Well, delta j says, keep the frequencies whose magnitude is between 2 to the j and 2 to the j plus 1. So again, basically, again, this is saying if you're in the lower end of the high frequencies, you've grouped them into sort of a smaller band. If you're in the higher end of the high frequencies, you're in a very large band because that corresponds to larger little j's. Again, this is just a hard cutoff. Analogously to the low pass, if we like, we can do this in a smoother fashion, which is not so brutal. And that gets us into convolution operators with wavelets. And so a wavelet psi is going to have Fourier transform psi hat j, which can be written as, say, psi hat 2 to the minus jk. The gist of all this is that the support of the Fourier transform of this function is going to lie approximately in this range of frequencies that previously we were cutting off. And so when we compute the convolution of x with this wavelet, we keep the frequencies approximately in this range, okay? And a wavelet transform then computes all of these different things. It computes the low frequencies of x via the low pass, which could be, say, convolution with a low pass filter. And it also keeps all of the high frequencies, but decomposed into these in this multi-scale fashion with, say, a wavelet transform. And so here's a picture of what's going on. Here again is our butterfly image. Here's the convolution with the low pass on the right for a fixed capital J with, say, sort of an intermediate sized blurring operator. And then here on the left are the wavelet coefficients that one obtains by convolving with the wavelets that one, well, can hopefully see here in this last row. So what we see here is that these wavelets, it's a little hard to tell, but these are more oscillatory than the low pass. They have, for example, 0 average, unlike the low pass. And they act as basically a multi-scale edge detector in the original butterfly image. Sort of here keeping sort of edge-like patterns at a larger scale, which have been blurred a bit because of the size of the filter, but then as the filter gets progressively smaller, and in terms of the frequency content keeps higher and higher frequencies of the butterfly image, acts more and more like a traditional edge detector in which all non-edge information is filtered out of the image and only the edge information is retained. And this can be, of course, refined with different types of filter constructions, which we'll describe here down the line. The thing about this representation as opposed to the low pass representation is that this is invertible. Everything that you need to know about the image is contained here in these maps. And you can take these maps and you can reconstruct the butterfly image. So we haven't lost anything. And one can sort of see that very simply through this representation. Now, we want to use these wavelet coefficients in our representation. We know that the low frequency ones are quasi-invariant to isometries. However, we cannot simply compose the low frequency operator with the high frequency wavelet operator. We're going to get a trivial representation which just maps everything to 0. So we need to transform these multi-scale wavelet coefficients. And the idea is to then apply a pointwise nonlinearity sigma to them. And for example, if we apply the absolute value or the complex modulus, if these are complex valued, if we apply the rectified linear unit, or if we apply a sigmoidal function, then you'll notice that after applying this sigmoidal function or ReLU or absolute value, we're going to get nonlinear coefficient maps that are non-negative. And if they're non-negative, this means that when we average them locally via the local averaging operator, which one can think of as sort of an average pooling operator in the ConvNet sort of naming convention, this is going to be a non-trivial map because if you're averaging a bunch of non-negative things, you can't get 0. And so this is going to allow us to then encode some of the high frequency content of our signal X, but in an invariant and stable fashion, unlike the original wavelet coefficients. And so here's sort of, again, an illustration of that in which we took the original wavelet coefficients, We then applied the nonlinearity here. So here, gray is 0, black is negative, white is positive. Here, black is 0, white is positive. These are non-negative maps. Here's the Fourier transforms of those original wavelet coefficients. Here's the Fourier transforms of these non-linearly transformed wavelet coefficients after, say, an absolute value nonlinearity. You can see what happens is that the high frequency information in the original wavelet coefficients, some of it gets pushed down into the low frequencies via the nonlinear mapping. And this in turn, and then you may also recall that it's exactly in these low frequencies in which the averaging operator extracts information, right? It's going to extract then information from these low frequency components of these non-linearly transformed wavelet coefficient maps. And you'll notice up here that this would have resulted in nothing because there's a hole here where the low pass works. Okay, so anyway, this then gives us the following representation consisting of the average of the original signal as well as the averaging of the non-linearly transformed high frequency components of the signal. What you'll notice now is beginning to look a little bit like a ConvNet. Indeed, we have a convolution here with some filters at different scales, followed by a nonlinearity, followed by another convolution, which we can really think of as like an average pooling operator. We can almost think of this as like a one-layer ConvNet. And in fact, and then here's sort of the types of maps that we get, which you can see all have this blurring quality to them to encode the invariance and stability properties, but which indeed, in fact, these ones here also are encoding some high frequency information of the original signal X. Now, basically the idea now is to iterate upon this logic. The idea being that even though we've used this nonlinear operators such as an absolute value to push some of the high frequency content of these maps down into the low frequencies, some of its information still resides in the high frequency components. If we have a complex learning task in which separating out different classes requires this sort of intuition analysis of subtle information, it's likely that we're going to need this information in order to come up with a high accuracy classifier, for example. That means that basically we need to sort of iterate and sort of find a way to push this information down to the low frequencies. That means we compute a second wavelet transform of these nonlinear maps, which then is going to decompose in a multiscale fashion the residual high frequencies that we see here. And we iterate and compute, which is all to say that we applied our nonlinear operator, which pushed some of its high frequency content down into the low frequencies. We extracted that on the previous slide, or we extract it right here. But then the stuff that's left over, we apply yet another wavelet transform, another nonlinear operator to push this information out here down into the low frequencies, followed by an averaging operator AJ, which encodes again the invariance and stability properties of the representation which we desire, this type of average pooling operator. And this now resembles very much a two-layer ConvNet. And in fact, here's sort of a schematic of what's going on, right? So here again is our butterfly image X. We extract via, say, a local average pooling operator some useful information from it that is both stable and invariant with respect to, say, isometries or diffeomorphisms and isometries, respectively. The remaining high frequency content is recaptured with a wavelet transform and then pushed down into the low frequencies via nonlinear transform sigma, the very low frequency content of which is captured with yet another application of the averaging operator, again, sort of a local pooling operator. Any residual high frequency information lost here is pushed on to the next layer, which is recaptured with a second wavelet transform, pushed down into the lower frequencies with a second nonlinearity, some of which is captured in a stable and invariant fashion via the convolution with this low pass, which again is like an average pooling operation. And again, one can iterate this logic even further, computing a third layer and a fourth layer and so on and so forth. So anyway, this is all to say, this architecture really arose out of these basic considerations that we espoused at the beginning of the talk. Anyway, here's this representation in a more compact mathematical form. And here now is the theorem of Malad that says, well, if you construct this thing and you use the absolute value nonlinearity, and you consider diffeomorphisms that are sort of generalized translations. In other words, they can be written as u minus tau of u, where tau of u, of course, depends on the location u. And we consider a diffeomorphism of this form. Then, and we look at the M layer, what we'll call wavelet scattering ConvNet representation of the original signal relative to the M layer scattering representation of the deformed signal, it has very nice stability properties. In particular, it has a form of quasi-translation invariance given by this term here, as well as a type of Lipschitz stability with respect to the diffeomorphism itself. And additionally, it's a rich representation of the original signal data because we've processed it through M layers of the transform, where at each layer we're successively recapturing more and more frequency content of the original signal X. Okay, so now in the remaining part of this talk, let me apply this theory in a few different contexts and give a few different little sort of vignettes. Here we're going to look at the problem of predicting either the ground state energy or the formation energy, the energy of an atomic system, which in terms of quantum chemistry or material science is modeled through quantum mechanics. And so in particular, what we have here is a three-dimensional atomic system in which the atoms have positions Ri, which are located in R3, and they have atomic numbers Zi. So 1 for hydrogen, 8 for oxygen, and so on and so forth. We can represent this atomic system as a three-dimensional signal in which we put just a little point at the location of each atom, and we raise that point to a height given by the atomic number. That's how we're going to think of this system. We're going to think of this as a supervised learning problem in which we're given a certain number of, say, molecules or atomic representations of materials. We're given their energies. Now we get a new molecule or a new atomic representation of a material. We want to predict its energy or some other related property. So this is a supervised learning problem, which if I'm focused on the energy means we want to estimate the ground state energy of the state X. And it fits into this invariance framework very nicely because it's physics. And of course it has then certain invariances. And in this case, it's with respect to translations and rotations in 3D. It's also very fundamentally a multiscale problem. Indeed, if I have a central particle here, it might have some nearby particles or atoms that are interacting very strongly with it. Maybe they're covalently bonded. But on the other hand, the atoms or particles at longer length scales also influence this central atom via weaker interactions, such as van der Waals interactions, or certainly long-range interactions like electrostatic interactions. So all of the different sort of ideas that we've talked about, invariance, stability, multiscale, play a fundamental role in this problem. For this, we designed wavelets sort of inspired by atomic orbitals from quantum chemistry, which means we're using spherical harmonics as well as then some type of radial function. We then compute the wavelet coefficients of this signal X, which represents the atomic state. It has a nice interpretation here in this particular problem because it means that we're emitting these waveforms from each atom in the system. Here are pictures of some of the wavelets themselves, and here's their sort of corresponding hydrogen orbital, and you can see the sort of nice correspondence between them. The difference being that in the wavelet context, we dilate these orbitals at different scales in order to capture multiscale geometric patterns of the arrangements of the atoms in the system. And so indeed, here's sort of some pictures of that, right? So here then we have the different wavelet coefficients at different scales and different atomic orbitals of an atomic system representing some type of material, which I'll describe here in a second, followed by a nonlinearity sigma, which I haven't described for you, but which is a sort of special type of nonlinearity that we designed to work well with these types of wavelets in order to encode rotationally invariant representations of the system, which is a non-trivial task in 3 dimensions. Anyway, you can see here the different scales of the wavelet coefficients along the horizontal, and the different types of wavelets along the vertical. And you can see they're extracting sort of interesting multi-scale geometric patterns of the atomic system, which all of these maps then are then aggregated or integrated over in order to get then an invariant coefficient with respect that's invariant with respect to translations and rotations, which is then given by these norms that you see here. And so here are the first layer coefficients, here are the second layer coefficients. Then we follow this up with a norm to obtain translation and rotation invariance. And we use these invariant coefficients then to form our model for the energy as a simple weighted linear regression. And we then learn these weights from the training data. We then applied this to different chemical databases of molecules, but more recently, we've also applied it to amorphous lithium silicon systems in materials science in collaboration with some materials scientists, friends of ours, due to the interest in using these for next generation lithium ion batteries. And so when one trains on a subset of these lithium silicon materials and then wants to predict the energies of new configurations of lithium silicon atoms, we find that we get very good performance in terms of the area here. So this is 5.5 millielectron volts per atom. What does that mean? Well, that's pretty good. If I was doing quantum mechanics, I might hope for, say, 1 millielectron volt per atom or less. But nevertheless, this is very much usable and is indeed in line with, say, recent neural network, fully learned neural network approaches to this problem. And furthermore, doing some additional tests, we found that these learned three-dimensional wavelet scattering models can even extrapolate to predict materials properties for which they were not originally trained. In particular, we looked at diffusion barrier paths, which consist of moving a single atom through the system in an optimal fashion. And we found that the predictions of our wavelets, of our trained wavelet scattering model, which was not trained for this task at all, agree pretty well with the quantum mechanical calculations. And we were also able to predict with good accuracy elastic properties of the material, which is basically consists of stretching and straining of the system and looking at the energy profile. And this turned out to work very well as well. So this is all to say one can use sort of a lot of human learning combined with some machine learning, as well as, in that human learning aspect, incorporating principles of ConvNets to rival even fully learned architectures and even do things which may not seem on the surface, well, do things that the model was not originally trained for, let's put it that way. Let me now shift to a bit of a different problem. Let me go back to image processing and not classification, but rather generative models. So here I'm looking at the texture synthesis problem, in which you're given a texture-like image, like these berries here, or these pebbles here, or these trees here. And the idea is you want to be able to generate a new image that is not the same image as the original one, but which has the same perceptual quality as the original. And so something like this image, or this image. And indeed, these are all synthetic images, not generated by us, but rather generated by these folks here, using basically using a pre-trained VGG convolutional neural network, which was trained on the ImageNet database, and then extracting statistics from this network, and then doing a gradient descent to find an image that has the same statistics as the reference image. So in other words, you take your input image, say the berries, you process it through the VGG network. Along the way, you're extracting different statistics of those filtrations, things like covariances. Then you start with a noise image, some Gaussian white noise image. You pass it through the VGG network. You observe, of course, that its statistics are different than the statistics of berries because it's not berries. And then you say, well, let me do a backprop and let me adjust the pixel intensities of my noise to match the statistics of the berries. And I do this back and forth many times, backprop, adjust the pixels, send it back through the network. Oh, its statistics still don't match. Backprop again, so on and so forth until I converge. And what they observed is that the statistics of a ConvNet are very powerful for characterizing different texture classes. Because when they did this, the image that they eventually converged to is this for the berries, this for the pebbles, and this for the trees. And they have more examples, of course, in their paper. But these images are very nice, right? They have very good perceptual quality in the sense that, yes, I can see these are very clearly berries, pebbles, and trees. But they're also not the same image as the original. Okay, so we were interested in sort of trying to understand this. So one of the things one observes immediately is that, well, in the VGG network, it relies very heavily, and this is some nice topological data analysis work of Carlson and Gabrielson, that the filters in the VGG network are very much reliant upon directional information. So they're not like omnidirectional filters like the ones we saw for 3D atomic systems, or even the ones I was just using to illustrate the butterfly image earlier, but rather they're encoding, they're edge detectors, but oriented edge detectors, as well as also some omnidirectional filters though. And so we then built, so my student and I, Chichen He, and I built then a type of mathematical model for this based upon the wavelet scattering approach that I just discussed at the beginning, in the first part of this talk, which incorporates both omnidirectional filters, but two-dimensional ones, sort of akin to the ones we saw for the atomic orbitals, but also incorporates standard directional filters as well. Unlike VGG, which uses nothing but very, very tiny filters, though, we used multiscale wavelet filters, right, as we discussed in this talk. And so here then are some of the results of that, comparing, say, the synthesis obtained with the VGG network versus the scattering network, as well as a classical approach to this by Portilla and Simoncelli from about 20 years ago. So the original image is on the left, the classical approach by Portilla and Simoncelli next, the VGG approach by Gaddis and collaborators third, and then the scattering, really like a very, very heavily modified scattering approach by Jit-Chen and myself here on the right. And you know, it's not perfect, but we see in some cases it's not quite as good as VGG. For example, the pebbles, certainly VGG does better. But in other cases, we see that the approach in fact surpasses even the state of the art. For example, particularly with respect to more rigid patterns like this and like this, in which case the VGG network struggles to reproduce that pattern. And then there's even complicated ones here where VGG does very well, and we actually do pretty well as well, although maybe not quite as good. Anyway, this is all to say that we basically didn't have to train this on 1 million images in order to get this result. We just had to sort of have a well-designed network, and which we're hoping can lead to additional mathematical understanding now that we've got this thing working. Here's just a cool image or cool plot, which shows, for example, on this one here, where you can see the neural network had a bit of some trouble reproducing the rigid pattern of the original image. The sort of learning process of our approach, which also early on in its learning process had the same issues. You can see it's warped and having some issues. But because of the multiscale nature of the wavelet filters, at least that's the hypothesis, is able to sort of sort this out with enough iterations, basically. And this is sort of how it looks in the very beginning, where you can see it's quite poor. But that's, of course, what the iterations are for. Anyway, I believe I'm running out of time, so I'm probably going to skip all of this. This is all to say that one can actually use these ideas for genuine inverse problems as well, in which you're trying to not just recover a signal that has the same perceptual quality as the original, but actually recover the original signal after it's been highly corrupted by several different nuisance factors, including random translations, additive noise, and even a random dilation. And this is of interest in things like cryo-electron microscopy and other types of real-world settings. Anyway, the punchline is that one can develop these ideas in this context as well, and one can solve inverse problems with them. In fact, again, with minimal learning, actually, but really just good old-fashioned sort of human intelligence and mathematics and engineering. But again, taking ideas from these convolutional style architectures and convolutional networks. And finally, then, again, I'll just skip over all of this, but I'll just mention it briefly. All of these ideas, as I mentioned, can in some sense be generalized to manifolds and graphs by using sort of the notions of graph signal processing or geometric signal processing on manifolds, and sort of the study of graph Laplacians and Laplace Beltrami operators, and the sort of harmonics, the eigenfunctions and eigenvectors of these, which correspond to the Fourier modes in the traditional setting, the Euclidean setting. So anyway, one can design wavelets on manifolds, or more generally filters. One can build these mathematical models on manifolds. And notably, one can even prove, and we have, these type of stability and invariance properties, but with respect to ConvNets designed on manifolds, indicating some kind of, what we would like to hope at least, is some universality to these ideas. Here's some numerical results. And again, on graphs, one can do the same thing. And again, perhaps surprisingly, still prove theorems even in the graph setting, again, about notions of invariance, this case with respect to permutations, and stability with respect to graph perturbations. Okay, so anyway, to conclude, I've introduced here this notion of a wavelet scattering transform, first introduced by Stéphane Mallat, but subsequently, which has been developed along many different avenues, some of which by ourselves, which extracts patterns from complex high-dimensional data by leveraging symmetry and invariance properties in the data, stability to diffeomorphisms, scale separation via, say, wavelet transforms, as well as nonlinear coupling of scales via these multi-layer cascades in the vein of a convolutional neural network. And by encoding these properties, indeed, the architecture of a ConvNet naturally arises, at least several different aspects of it, the use of convolution operators, the use of nonlinearities, and the depth, right? The sort of application of these operators repeatedly, leading to some mathematical understanding of these architectures, particularly with respect to stability and invariance properties. Less so with respect to the expressivity of the network, although that's where empirical results come into play. Nevertheless, there's a lot of open mathematical questions there. Furthermore, this quote unquote mathematical logic extends, perhaps surprisingly, to manifolds and graphs. Now that I skipped over, but hopefully you'll take my word for it, and I'd be happy to discuss that offline. And on the other hand, it's more than just a mathematical model, at least we'd like to argue that. In its own right, indeed, it's a useful tool for high-dimensional learning problems. We saw ones in physics. We saw the image generation with texture synthesis. I mentioned inverse problems as well. So anyway, it's a nice model, both for the mathematical side of things and on the empirical side. And with that, I want to thank you very much for your attention and time today.
Thank you, Matthew. That was a great talk. The floor is open for questions.
Hi, Matthew. This is Paresh. Thanks for the talk. I just have like a few questions. So in the texture synthesis, do you give convergence guarantees for gradient descent algorithm which you used? And is there any motivation for Gaussian distribution? Can we do it like with, I don't know, a Laplacian or some other?
Right. Yeah, those are really good questions. There's no convergence guarantees. And I should actually mention that we actually replaced the gradient descent in our case with a type of projection algorithm. We did some math basically to build a ConvNet, which we could invert at each layer, which would have enabled us to do anyway, a modified way of synthesizing, of adjusting the pixels based on a type of projection pursuit. But even that doesn't have a guarantee for convergence. So there's no guarantee of convergence. And indeed, that's generally an open problem in almost any texture synthesis algorithm. So that's not to give us an excuse or anything, but I think it's a great question and certainly one that remains open. Regarding the use of initialization with Gaussian white noise, certainly you can pick something else. In fact, we've also often picked like a uniform distribution. The motivation there is that in theory, what you would like to do is you specify the statistical profile of the reference image through phi of x. And then you say, I want to find a new image that has the same statistical profile. And this then generates for you a set of images. I mean, implicitly generates for you. Of course, you don't have access to it. But it implicitly generates for you a set of images with the same statistical profile as the reference image x. And intuitively, you would probably like to sample from this set of images with the uniform distribution, and that every image has equal probability, because that sort of gives you the most insight into the power of the representation itself, in the sense that there's no other factors coming into how the image was generated, which means that basically you're trying to sample from the Gibbs distribution, which is known to be very computationally difficult. And so the hypothesis or ansatz or whatever you want to call it is that, well, if I just start with something that has sort of the maximum amount of randomness in it, like a Gaussian white noise, and I then do like a gradient descent, this will be sort of approximately an approximately unbiased way of sampling from the set of all images with the same statistical profile. Although again, it is not exactly that, certainly. But
got it. Yeah, I just have a follow-up question. So in the proofs you mentioned, do you prove those theorems with you haven't mentioned the proofs, but do you prove those theorems with Cauchy-Schwarz kind of inequalities, or?
Let's see. I guess it depends which type. So in the it's more like you can do some analysis. Sorry, I probably don't need to flip around here, but to prove the theorems, you can do some analysis that sort of reduces the problem down to a one-layer problem if you design the network appropriately. And then in the one-layer stability proof, you're basically looking at issues of, let me try to at least bring up one theorem here, right? You're basically trying to then bound the commutator, the operator norm of the commutator of, say, the diffeomorphism operator and the operator that corresponds to like one layer of your network, which involves, it depends on the context actually. So in the original Euclidean version by Stéphane Mallat, this used what are known as like approximate orthogonality arguments from like classical harmonic analysis. In the case here of manifolds, we had to use basically mathematical techniques coming from spectral geometry, so the analysis of eigenfunctions and eigenvalues of the Laplace-Beltrami operator in manifolds.
So is that the motivation for infinity norm?
Oh, here?
Yeah.
Yeah, this one. So yeah, that's a good point. So here, what's going on is the infinity norm here is. So, okay, so in this one, we're taking a diffeomorphism zeta, and we're actually decomposing it as a zeta 1 and a zeta 2, where zeta 1 is an isometry and zeta 2 is a diffeomorphism. Now, of course, I could just say the isometry is the identity and zeta 2 is just zeta. But in fact, if you have other such decompositions, you can use those too. And so the idea here is that this is like the isometric component of the diffeomorphism. And so in particular, then what we're interested in is sort of the maximum displacement that this can induce on, say, the signal supported on the manifold. And what this says here is that we can control it because we get to pick J. And in particular, we can send J to negative infinity if we like, which would correspond to removing the effect of any isometric transform on the data. On the other hand, this component here we cannot remove. This is the part of the diffeomorphism that no matter how we decompose it, we always have left over. But at least we have a type of stability with respect to it. In terms of the use of infinity norms, yeah, I mean, this one is completely fine in the sense that we have the control over it. This one here is what the math sort of led us to be honest. But actually in the paper, we discuss other notions that one might want to use, say on the manifold case. In the graph case as well, the notion of stability that we have is by no means necessarily the right notion. It's a notion, but I think it's certainly debatable if it's the right notion.
Got it.
Matthew, thank you. We have one more question. I want to make sure others get a chance to ask questions.
Oh, sure.
We have Henry, who have posted the question in the chat. Henry, you want to ask the question? Or maybe I
can read it. Let's see.
Okay, if you can read it.
Sure. Yeah, I brought it up. In the texture synthesis slide, when you mentioned that the model is iteratively trained, how the method handled the covariance based on the backpropagation. Okay, right. So I partially alluded to this in that well, it turned out that we didn't use backpropagation for this. We used a different type of algorithm, a projection-based algorithm. But let's see, how does the method handle the covariance positive definition based on the backpropagation? Right. So the way the projection algorithm works is that it updates the filter responses of the current synthesized image, so like at this iteration, so that its covariance statistics at that layer match the covariance statistics of the reference image at that layer. And then the iterative part comes in the sense that you cannot match all the layers at the same time that way. So then it iterates through the different layers. And sort of one pass through all the layers is what we call a single iteration. And so then this is also then very much related to the convergence issues, because any such algorithm, it would be a priori would not necessarily have to converge, although empirically we show that it does a pretty good job. But in terms of ensuring that the statistics satisfies certain properties of the statistics like positive definiteness, at each sub-step of the iteration, this is going to happen automatically in that the projection will project the coefficients in such a way that they are forced to match the reference statistics. But once you then match a subsequent step, a subsequent set of statistics in, say, another layer, certainly you can mess up the ones from the previous layer. And we don't have any guarantees along those lines at this time. It's a very good question as well. It's a very hard problem too.
Thank you. There is one last question from Daniel Millen. Want to ask?
Yes, thank you. This is Daniel Ocampo. I wanted to ask, back in the application on material science, you talked about finding a Wavelet function that deals with the rotational invariance of an system. Is this part of the overall same net you guys found, or is it a separate, different, because you talked about it not being trivial, right? Dealing with that rotational invariance. So I was wondering how specifically you guys dealt with that.
Yeah, we dealt with that very specifically. So in 2 dimensions, rotation, equivariance, and invariance can be done with directional filters that we saw in the texture synthesis problem, because the rotation group is one-dimensional, and you know that if you're rotating your wavelet along an angle of rotation, and then your input happens to be rotated as well, you can work out very easily sort of what's going to happen. In 3D, you can actually do the same analysis, but the problem becomes your rotation group now is 3-dimensional. And in order to get rotation invariance through directional filters, you basically are now having to approximate like a 3-dimensional integral over the rotation group, which is doable, but is inefficient, at least in our experience. And furthermore, is not precise in that this integral approximation is not exact. So the solution, which is also done by other groups, even in the neural network literature for these types of problems, is to use filters which are based upon the polar representation of U. So in other words, we decompose U into its radial component and its angular component. And I've sort of hidden it here, but there's two angles, of course, because we're in 3D. And for the angular component, we use spherical harmonics, so the harmonics of the sphere. And these filters are not rotationally equivariant either, meaning that if I were to rotate, I mean, in the sense that if I were to rotate X, the convolution of X with these filters would actually, what would happen is it would rotate the space variable U. That's like a classic equivariance property, but it would also redistribute information along the M index. But that at least we understand because of the use of spherical harmonics. And it turns out then that there's a nonlinear way of taking these coefficients and collapsing the information along the M index. And that's what this nonlinearity does. And so I can just write it down for you even, but basically the idea is that if I want to get a rotation equivariant representation, so in other words, one that if I were to rotate the input, the output is rotated in the same exact fashion. What I do is I take all of the different wavelet coefficients over the M index for all other indices fixed. So M here is running from -L to L. And I then compute the modulus of them. And then I square it, I add it up, and I take the square root. And one can show that if I were to rotate X, then this is equivalent to taking the same nonlinear coefficients and just rotating them, which is a classic like equivariance property, which then means that when I compute the norm, I get a rotationally equivariant representation. So no, in fact, we really think about it for a while in the early goings of this several years ago, after basically banging our heads against the wall trying to do directional filters because it's coming out of computer vision. But which in turn was a very natural solution, in which, yeah, other folks also use for the processing and design of their networks for such systems.
Thank you. So could we say so far that the approach of converting those Cartesian coordinates into some, maybe I've seen some people using symmetry functions or Gaussian descriptors to account for that rotational invariance would be more efficient, you think, as compared to these filters?
If you Gauss type filter, then just based on the distance between particles, right, then certainly that's going to work for you. The thing it's not going to have is like the subtle angular information that this type of filter has. So the main bottleneck of this approach, which is something we're addressing in current work, is the fact that we voxelize everything, right? I mean, we have this representation of the atomic system in terms of just points located at the locations of the atoms, but then we compute these maps, right, which are supported in a box supporting that system, and they're supported on every voxel. And that, to me, is actually the bigger bottleneck than, say, the conversion from Cartesian to polar coordinates. And something that more efficient networks do, that what I've presented here does not do, is they don't have any voxelization. They build their network directly to work directly on the particles themselves, and there's no like background voxelization of the system. In that case, then all of your operations are scaling directly with the number of particles and no sort of background grid. And so that's something that we've been currently working on ourselves as well. And I think that's where the biggest speed up is probably gained. At least my impression is the conversion to a spherical coordinate system for your n particles is not a big deal, and the spherical harmonic evaluation can be done pretty efficiently too. So Yeah.
And then Matthew, I think there are a lot more questions. This is a very interesting talk, but I think I would request folks to reach out to Dr. Hirn. I believe he has posted his email address at the beginning of the talk. So please feel free to reach out to him for further questions. And the talk will be posted on YouTube channel pretty soon. So you'll be able to revisit and see if that clarifies some of the questions you have as well. I know there are a lot of hands raising still, but I think we are at 12:10 right now. Thank you so much for your time, Dr. Hirn.
Oh, thank you very much for the invitation. And certainly, if anyone wants to email me, they're more than welcome to. My email is on my website, and I think indeed it was on the first slide. But anyway, it's readily available online. So please feel free to email me.
Thank you. Bye.
Bye, everyone. Thank you very much.